Broadcast, unknown-unicast, and multicast traffic is special in your network. They share the same thing, which is one packet from the source may be forwarded to multiple parts of your switches. Because of the nature of these three types of traffic, they may cause problems. Sometimes it may even make your network unusable. Three of them are referred as BUM, B-U-M. To control BUM, a common way is to do throttling, which is exactly what Ubiquiti implemented in their UniFi switches. In UniFi Network Controller, for port setting, if you click on a port, it can show you a list of options. You can see storm control here. If you enable it, it will list three additional settings: unicast, multicast, broadcast. For some reason which I don't understand, Ubiquiti put the wording unicast here instead of unknown-unicast. But I know in their legacy UI or even previous versions of network controller, it had always been unknown-unicast. But anyway, here what it really says is unknown-unicast. Okay, you have three different types of traffic to control. So in this video, let's explore them. We will discuss what's unknown-unicast, how this storm control setting can reduce the impact of unknown-unicast, and whether the same setting works for regular unicast. Then we will discuss how the storm control setting can work with multicast. And what about IGMP snooping, which is also used to control multicast. In the third part, we will discuss how the storm control can work with broadcast. Okay, let's get started. This is my lab environment. I have a UX3 Pro as the gateway, two UniFi switches. In the first switch, I connect a Linux virtual machine. It will try to do some damages. And then in the second UniFi switch, I run another Linux machine. It will be minding its own business, but it will be bothered by this troublemaker. Okay, and then to understand how the packet forwarding works, I run two separate Wireshark sessions, one to monitor this particular troublemaker's port, and the other one to monitor the victim's machine. Okay, now we are ready to talk about unknown-unicast. Let's first understand what's unicast. Here I show you two terminals for the victim machine. Let me see what's the IP address. It's .1.111, right? From the troublemaker, I can ping it. How the troublemaker even knows how to send the packet to the victim, it relies on ARP table. I can show you the ARP table in this way, IP neighbor. Okay, for the .1.111 machine, this Linux machine knows it has this MAC address. So that's why it can send out the packet on layer 2 to this machine. But that's not enough, because when the packet reaches the switch also needs to know the mapping between the IP address and the MAC address. So in the left side terminal, let me SSH into the first UniFi switch. Then go to command line interface, run this command, show ARP switch. Okay, so this switch knows for this particular IP address, this is the MAC address. If you compare the left and the right side results, you can see it's the same MAC address. This right side Linux machine send a packet to this switch, and the switch also understands the ARP in this way. Here it maintains for this particular MAC address which interface it connect to. So that's why this switch can forward this packet to the interface 25. That's how the regular unicast works. Then what is unknown-unicast? Unknown-unicast traffic consists of unicast packets with unknown destination MAC addresses. By default, in this situation, the switch will flood these unicast packets that traverse a VLAN to all interfaces that are members of that particular VLAN. Forwarding this type of traffic can create unnecessary traffic that leads to to poor network performance or even a complete loss of network service. This flooding of packet is known as a traffic storm. In my lab environment, to simulate such network storm, I need to first create some unknown unicast traffic, which means I need to make up a MAC address and somehow insert it to the ARP table. To do that, from the troublemaker machine, let me see what's the current link. So I can see the interface name is called ENS18. I'm ready to add a made-up MAC address to the ARP table, but before that, let me show the current ARP table. It's super simple, right? By the way, you see different content compared with what we just did about the regular unicast testing because I just rebooted this Linux machine in order to have a fresh start. Okay, now I can add a made-up entry here in this way. What I'm saying is for IP neighbor, let me add a neighbor with this IP address, this made-up MAC address. You can see apparently it's a fake MAC address, right? And using this device, where I got this device from the IP link, right? So this is my Linux virtual machine's network interface name. Okay, let me run it. Okay, it's done. Now if I see the IP neighbor again, you see this newly added entry. It shows it's permanent because I added it manually. It will be here until you either change it or restart your machine. By the way, I don't have a device in my network with this IP address. This ARP entry is completely fake. In the SSH session for the switch, if I run the show ARP switch command again, you can see it's not changed. It doesn't have the fake ARP entry I made up in the Linux machine. So the switch has zero information about the fake MAC address and the fake IP address. This time, if I try to ping this IP address, the ping will fail for sure, right? But from here, you don't really see where is the unknown unicast. To observe it in the lower part of the screen, in the two Wireshark sessions, let me monitor the traffic. As shown in the diagram, the left Wireshark is monitoring the troublemaker. The right side Wireshark is monitoring the victim machine. Let me start monitoring. Then from the troublemaker machine, let me ping the fake IP address again. Okay, some pink entries show up in both sessions, right? Let me stop capturing. Let's see what happened. From the troublemaker, from its own IP address, it tried to ping this fake IP address. And if you check the details of the packet, you can see destination MAC address is the ridiculous fake MAC address I just made up, right? It makes sense because this Wireshark captured the packet for this part for the troublemaker, right? But interestingly, the same ICMP packets also show up in the second Wireshark. The second Wireshark captured the victim. So what the troublemaker was doing, ping this fake IP address, it has nothing to do with this victim. Normally, this victim is not supposed to see this type of traffic, which has nothing to do with itself. But for this unknown unicast situation, it did see them. Why? Because the switch doesn't know how to handle this packet, so it will simply flood every single parts. Because I'm doing the testing in default network, so all the parts will be flooded, including this part, which is connected to the victim machine. Just to compare, let's see how a regular unicast works. So from the same troublemaker machine, let me ping the UniFi gateway. Stop capturing. See the difference? The ICMP packets only show up in the left side Wireshark, which is monitoring the troublemaker. From the victim part, we don't see those ping messages. Why? Because that's how regular unicast works. The switch will not forward the packet to victim part simply because the packets have nothing to do with it. Someone may think, what a big deal. It's just several useless, harmless, simple packets, right? Why bother? So now let me simulate a traffic storm by flooding the system with unknown unicast packets. So let's confirm we still have the fake ARP entry in the Linux machine. Okay, yes, it's still here. Then in the two Wireshark sessions, start capturing. So in the troublemaker machine, let me run this command. hping3 is a very handy tool when it comes to network testing. I'm going to flood the network and using this fake IP address. Flood means it doesn't wait for the response and it will send the packet as fast as possible without wait. It will create a situation to stress the machine and the network resource. So let me start running it and you can observe the effects in both Wireshark sessions. Okay, see, even the Wireshark cannot respond smoothly. It is still struggling and it is still capturing. That's enough. Let me kill the hping. And you can see even though I already killed the tool, the two Wiresharks still need some time to catch up. Okay, now they both go back to the quiet situation, right? Let me stop capturing. Let's observe what really happened. Let's check left side Wireshark first. It captured the troublemaker machine, right? Starting from this time, the system is first flooded with the same type of packet from this troublemaker Linux machine to the fake IP address, and from the first two columns, the sequence number and the time, you can see within 1 second there were tons of packets. Thousands, tens of thousands of them within 1 single second. If you check the right side situation, it's identical to the left side. Even though this victim machine is in another switch, it has never asked for those flooded network packets. It still received them. And again, from the sequence number column and the time column, you can see it's the same situation. So it received the same packets which were sent out by the troublemaker machine. You can imagine during that short period what the victim machine experienced. Now you see the problem in action. It is a traffic storm caused by unknown-unicast. Then let's see how we can address it. In UniFi network controller, I go to the ports setting. On the overview screen, you can see port 17 is showing active. It's connected to the troublemaker machine. And for port 19, you can see the small I icon. It is doing the port mirroring to 17. That's why I can run Wireshark on the port 19 to see what's going on with the troublemaker, right? Then if I click on port 17, go to the storm control setting, I enable it. Because here we are talking about unknown-unicast, so I only enable the unknown-unicast. You can see by default, it's showing 100 packets per second. This is already the smallest number, so you can increase it, but you cannot decrease it. Let me accept this default value. Let's see whether this throttling setting will be effective. Apply changes. Then in the two Wiresharks, let me start capturing. From the troublemaker machine, let me run the exact same hping3 command to flood the fake IP address. Start it. Okay, so you can immediately see the difference. From the left side, you can still see the super busy network traffic. And from the first column, the number, you can see the number is increasing crazily, right? But from the right side, which is monitoring the victim part, you can see it's only increasing pretty slowly. In fact, exactly 100 packets per second. So you can tell from the number column and the time column. Our throttling setting for unknown-unicast successfully eased the pain for this victim part when it comes to unknown-unicast. Let me stop capturing and let's discuss what really happened. So remember, the only change I make is to the port 17. I didn't change port 7, right? That's the first thing I want to point out. Storm control setting, the granularity is per port, not per switch, not per VLAN. You only change the setting for the port which is connected to the troublemaker. You don't need to change the port which is connected to the victim. The second thing is, even though I change the port 17 storm control setting, you can still see the exact same busy flooded unicast packets for the port 17. To put it the other way, you change port 17 storm control setting, it will change the switch behavior when it comes to how to forward the unknown unicast. But the switch itself cannot really prevent the troublemaker from sending out those flooded packets. That's why from the left side Wireshark, you still see the same busy flooded packets, but it won't really bother other machines anymore because we already successfully throttled the traffic. Okay, I believe now it's very clear about how the unknown unicast throttling work for storm control. Before moving on, let me answer one natural question: whether the same throttling setting applies to regular unicast as well. Because anyway, for some confusing reason, Ubiquiti decides to put unicast here instead of unknown unicast, right? It may give you the illusion that the same setting applies to all unicast packets. Let's do a very simple testing to confirm that. Let me start capturing. Then from the troublemaker machine, let me run the similar hping3 command, but this time the target is the victim machine. It's not the invalid fake IP address. This type of command will generate flash of valid unicast packets. Let's see whether the throttling setting still works, right? You see the effect already, right? In both Wiresharks, you see the busy flooded packets and they have similar packets count. So the throttling setting doesn't apply to this valid unicast scenario at all. Okay, now let's move on to storm control multicast. A very simple use case scenario for multicast is IPTV or video streaming. So in this lab environment, I'm going to run a multicast video source as the troublemaker and then another machine as the multicast receiver. So first, from this troublemaker machine, let me start a video multicast. By the way, at this moment, if we check the port 17's storm control setting, you can see it's disabled. Okay, now from the troublemaking machine, let me start a streaming. I'm using one of my own videos just for copyright reason. To set up streaming, I'm going to use RTP using this multicast group IP address using this port. Apply. Before I start streaming, let me start Wireshark capturing. Okay, they both started. Click on the stream button. You see the same thing is happening in both Wireshark sessions. So you see tons of UDP packets which are produced due to this multicast video source. Even though now I don't have any multicast receiver which is receiving the video yet, but the multicast packets are being forwarded to all the ports. Okay, if you do want to control the multicast packets, you can enable the storm control for multicast if you want. Let me do it. Enable storm control for multicast. Enable it. Accept the default 100. Apply changes. Then if we go back to this multicast video source, now let me restart the Wireshark capturing. Then from the video source, let me start streaming again. Okay, now do you see the difference? So if you check the first column, the packet number, you can see in the left side, it has much more packets than the right side. The conclusion is in right side, the victim machine, it does have the multicast packets reduced, right? That's the effect of the storm control. But does it really do anything good? Because the reason we want to start the multicast video streaming is to receive the video from the victim machine, right? At this moment, with the storm control enabled for multicast, let me try to do the multicast receiving from the victim machine. This is the victim machine. Let me start receiving. You can see it's struggling even connecting to the source. After waiting for dozens of seconds, it's still not successfully connected. So basically, the storm control already disrupted the normal multicast video streaming, right? In fact, in this kind of multicast video streaming scenario, instead of using the storm control, you can simply enable IGMP snooping. That's the proper way to control the multicast traffic for video streaming. Of course, multicast doesn't equal to streaming, right? There are other multicasting scenarios. Maybe you can find find a proper scenario to enable the storm control. Okay, this is a short one. Let's move on to storm control broadcast. For broadcast, it's very easy to understand because you can easily create a broadcast storm by simply pinging the broadcast IP address. So let me start capturing. Okay, from the troublemaking machine, let me use hping3 again. This time, I'm going to use ICMP just to simulate ping. Similarly, I'm going to flood the packet. This time, the IP address I'm going to use is the broadcast address for this particular subnet. Okay, start it. See, in both Wireshark sessions, we see the equivalent amount of packets being flooded, right? Because now we don't have the storm control enabled for broadcast yet. Let me stop everything. Go to UniFi network controller for port 17. Enable storm control, enable broadcast, accept the default 100 packets per second, apply changes, then restart capturing. Okay, then run the exact same command from troublemaking machine. You see the dramatic difference between the two Wireshark, right? In the left side, it's the same flood of packets, but in the right side, you see exactly 100 packets per second. So the damage is dramatically reduced already. Okay, this is the end of the video. Thanks for watching.